start with the first seminar of this semester, the seminar series. For those of you that are COSI students, here is the sign-in sheet. Today we'll have Professor Kapteyn going to talk about ultrafast coherent X-rays and applications in imaging. Professor Kapteyn got his PhD from UC Berkeley in 1989, and then became a professor at Washington State University. He moved to the University of Michigan, and in 1999 he started his tenure here at JILA and the physics department. He's the recipient of many awards, including the National Science Foundation Young Investigator Award in 1992, the Optical Society of America Adolph Long Medal in 1993, and is a co-recipient with Professor Marek Monet of the 2009 JILA Award in Ultrafast Science and Technology from the American Chemical Society. He's also a fellow of many societies like the OSA, APS, and AAAS, and he's one of the founders of coherent. Today, his talk will be about, he's a pioneer in ultrashort lasers and its applications, and his talk today will be about one of these applications of the ultrashort lasers in imaging. So thanks, Professor Kapteyn. Welcome.
Okay, so I think this microphone works, does it?
Yes.
Yeah, great. Well, thank you very much, Ariel, for the gracious introduction. It's nice to have a nice, intimate seminar, so I didn't try to pack it too hard, although that might mean it's going to take the full hour anyway. But do feel free to interrupt me as I go along if you have questions. So first, I wanted to start with some of the students and collaborators who are working on this project. And it's specific that some of the current students working on this are Daniel Topnick-Schaff, who's working on some of the source things I'm going to talk about. Daisy Raymondson is working on the lensless imaging that I'll talk about, and also Richard Sandberg, who just very recently finished his PhD and moved on. And a number of other students listed here. Also collaborators. We have collaborators at UCLA and John Lane Yao's group. Bill Schlatter is listed as Stanford and DAISY. DAISY is a free electron laser facility in Germany, and he actually came and visited us in the week between his employment at Stanford and at DAISY. So that's why I listed both ways here. Also Jorge Roca's group, Jorge and Carmen and Mario Marconi at Colorado State. That's part of this engineering research center that we work with them extensively on. And also part of the ERC is the group of Dave Atwood and Eric Anderson. And in specific, Ansik Dinawat did some of the samples I'll show you for the imaging. Finally, also Keith Nelson at MIT. Okay, brief outline of the talk. First, I'm going to tell you a little bit about how you can generate laser light beams of light at short wavelength using something we call extreme nonlinear optics. You'll see why we call it extreme when I start to talk about it. Then I'll move on to using this laser-like light source for imaging systems, and this is really where it touches on the topic of COSI. It's a computational lensless imaging technique. Then I'll motivate a little and tell you about work that we're doing to extend these light sources to shorter and shorter wavelengths, which means wavelengths in the soft X-ray or possibly even the hard X-ray region of the spectrum. still using tabletop light sources, and I'll touch a little bit on a number of applications. So the theme of our research group is that we're making coherent X-ray sources. And the reason we do that is because X-rays have proven to be very useful, a unique tool in science and technology. And a good way of illustrating that is a lot of money has been spent in the last few decades building synchrotrons where you don't use the electrons in the synchrotron directly, but you use the X-rays that are generated when you bend an electron beam. And you get a series of so-called beamlines that, and this is an illustration from the Advanced Light Source website at UC Berkeley, at Lawrence Berkeley Lab. And these are different beamlines and the types of applications that these X-ray beams are used for. Things like surface science, chemical dynamics, photo emission, also protein crystallography and biomicroscopy, and also things like atomic physics. So wide variety of applications. One of the real problems with these synchrotron light sources is that they're big. They're very big. This is a picture of ALS. Those are cars down there. This was actually built under the dome of one of the early synchrotrons that Lawrence built in the 1950s, and they sort of got it and put the synchrotron there. So what we like to do is develop tabletop light sources that can do a lot of the same things that are done at synchrotrons, but also they might be able to do some things that synchrotrons can't do as well, like very high time resolution. And the way that we do that is we use a physical process called high harmonic generation. This is what we call our extreme nonlinear optics, and it's nonlinear optics in that you're taking a laser beam, so you focus a laser pulse into a gas of atoms or molecules, and you focus at intensities of about 10 to 15 watts per square centimeter, which, if you calculate the electric field strength that corresponds to, it's very comparable to the electric field that binds the outermost electrons in an atom to the atom itself. What you end up with is a process where the electric field of the laser rips an electron out of the atom. The electron then starts to oscillate, and if it comes back and re-encounters its parent atom, it can recombine with it. And if it does that, it emits the kinetic energy at the time of the so-called recollision as a short wavelength photon. Now, the beam that you get out is fully coherent. You're driving this process with coherent light, and the electron responds coherently. That means you get a forward-directed beam that looks just like a laser. But if you calculate the energy range that you can get from this process, you generate a broad spectrum of light that goes from the UV region of the spectrum all the way up to KV type photon energy. So covers the so-called extreme-ultraviolet and soft X-ray regions of the spectrum. Some of the other characteristics, you have a very short pulse duration because you're driving this with a short femtosecond pulse. That's the most efficient way of doing it because you're destroying a nonlinear medium, and you need high peak intensity. So you can get that best if you just use a short pulse. It's the largest intensity to pulse energy ratio. You get a series of harmonics that correspond to odd numbers of photons of the driving laser. And you can calculate the range of photon energies through this so-called cutoff rule. This expression you can actually derive from classical physics. It relates to the wiggle energy of this electron at the time it recollides with the atom to generate the X-rays. it turns out that one very, very nice characteristic of this cutoff is that it's linearly proportional to the intensity of the laser. So you want higher photon energies, 200 eV instead of 100 eV photons. You only have to turn up the intensity of your laser by a factor of 2. Now there's some catches on that, and I'm going to talk a little bit more about that, but the fundamental scaling here is dramatically better than any other way of generating coherent X-rays. For example, X-ray lasers, if you just make a laser at soft X-ray wavelengths, turns out that the amount of power that you need as a function of the photon energy that you get out goes is about the 5th power as opposed to here's the 1st power. Now, to do this right, you need to phase match the process. Any nonlinear optical process needs to be phase matched, and all that means is that this driving laser is propagating through your gas. Gas is an extended medium, and if the speed of light of the driving laser and the generated X-ray signal are different, you'll end up with a situation where you get constructive and destructive interference as the thing propagates. What you want is to have exactly the same speed of light for the two. And then the signal builds up along the propagation here, and you can have a bright beam. You can set up phase matching for high harmonic generation, and a very good way of doing this is to do the high harmonic conversion in a waveguide. And these are very simple waveguides. They're just hollow glass tubes, but you guide the light through total external reflection off the walls of the tube, or near total. It's not actually total external reflection, but it's external reflection from the walls of the tube. You can keep a high intensity, fill the center of this with gas, and if you operate at the right pressure, you get a phase matching, which means the phase velocity of these two waves is exactly the same. You get a buildup of signal that's still limited, and it's limited by the fact that the light you're generating is at photon energies that are absorbed by the gas. So the background absorption limits the conversion. For example, at 50 eV, which is where our brightest light is, it's about 10 to the minus 5 if your laser gets converted into this extreme ultraviolet region of the spectrum. But we're using lasers with millijoule type pulse energies, so that means you can generate nanojoules of light, which is a large number of photons, something like a billion photons per pulse, and you can do it at kilohertz or even up to 50 kilohertz repetition rates. The result is exactly like a tabletop X-ray laser, soft X-ray laser. And the flux in the microwatt range that you get is sufficient for a variety of applications, including imaging. The other nice thing, if you set this up to be phase matched, is that the very high coherence of the laser that drives the process imprints itself on the X-ray beam. So this, for example, is a CCD image of a beam that out of this hollow waveguide. It's actually a Gauss, it fits to Gaussian to the noise floor of the CCD, which is 4 orders of magnitude. And if you measure the coherence through double pinhole measurements, you also see that you get very excellent coherence of the beam. Now, these beams are useful for a broad variety of applications, and these panels here illustrate some of the things that we've been doing in our labs. There's interesting molecular dynamics that you can extract from the high harmonic generation process itself, and there was a recent article in Science that we did where this was the cover illustration. This was in November 2008. Also surface science, you can look at dynamics of atoms and molecules on the surface by ejecting electrons from the surface with these very short X-ray pulses. These other topics at the bottom here I'm going to talk about. Mainly I'm going to focus on the use of the spatial coherence of this light for imaging, since that's the most relevant for this, this audience. Before I talk about our work, I'm also going to give you a little bit of background on soft X-ray microscopy. So if you want to make a microscope that has very short, very high resolution, one way of doing it is to use very short wavelength light. It's a very good way of doing it. You just, rather than try to defeat the diffraction limit, you work with it and make the wavelength of the light that you're using shorter. The problem with that for X-ray microscopy is that once the wavelength of the photons is short enough, the photon energy is high enough to become ionizing radiation. And in the soft X-ray region of the spectrum, all materials absorb very, very strongly this range of wavelengths. That means that there's basically no refractive optics. You can't make a lens to make a microscope with, but there are other alternatives. You can use either diffractive optics or reflective optics. Diffractive optics are things like zone plates. So if you have a light source and you simply block some spatial regions and allow other spatial regions to go through, you can diffract light from this structure and end up with a focus down the line. And I'm not going to go through the optics of a zone plate, but effectively you get a fairly inefficient lens. It's usually about 10% efficient in refocusing light. But it is a structure that you can manufacture pretty well, and people have been very successful using diffractive optics to make soft X-ray microscopes down to about 15 nanometers resolution. You can also make mirrors in this wavelength range. So if you can make mirrors, you can make a reflective microscope. This works as well. It generally is more difficult to align, so that the resolution in reflective microscopes has typically not been as good as in diffractive microscopes. Both of these techniques you generally use in incoherent illumination. It's like a typical microscope. You use a light bulb, not a laser, to illuminate the object. Because if you use the laser, you get a lot of diffraction, interference effects that can obscure the image. This just says a little bit more about diffractive microscopy. In a zone plate imaging, the resolution that you can get is limited by the aberrations in the zone plate. And in fact, it ends up being directly related to the smallest feature size that you can make in one of those zone plates. So if you can make dark and light stripes spaced by 15 nanometers in your zone plate, you get about that same 15 nanometer resolution in your image. And this paper actually is the one that showed that they can go down to about 15 nanometers. But it's difficult to do better. These zone plates are made with E-beam lithography. They're pretty much at the limit. The one they use at Berkeley to make these zone plates is the best in the world. You could use shorter wavelength light, but you wouldn't get any higher resolution. Now, another very useful aspect of doing microscopy with soft X-rays compared with, for example, electron microscopy, is that you can actually penetrate a reasonable amount of material and image things like single cells which are a few microns thick. You can image those with soft X-ray microscopy. So that's kind of our ultimate goal. But very recently, people have started playing with a new technique for imaging that's very, very well suited for this region of the spectrum. It's called lensless imaging, and it's a computational imaging technique. Experimentally, it's pretty simple, and that's why it's so useful for soft X-ray imaging. What you do is you take coherent light and you illuminate a sample with the coherent light. And then all you do is you let the light propagate. It hits some detector, a CCD detector, and you get some blobs, basically. If you look at these diffraction patterns, there's nothing intelligible in the light. There's nothing intelligible to us in the light pattern that scatters off the object here. But what you do is you take that data and you do so-called computational phase retrieval on it, and you reconstruct what this object must be if it results in the scatter pattern that you observe. Now, the way that you do this phase retrieval is illustrated very briefly here. You get some sort of diffraction pattern, and there's one constraint that you apply to this experimental geometry that's required, and that's that your object here has to be isolated. In other words, it has to be an object surrounded by nothing. If it's a continuous illuminated area here, the scatter pattern can't be deconvolved. But if it's an isolated object, and it's easy to isolate, all you have to do is put a pinhole there so that light only goes through a limited region of space. Then what you do is you take that diffraction pattern, you do in your computer, you do a Fourier transform of it, and you get something that might bear some resemblance to what the object should look like. Because after all, scattering is just an optical Fourier transform. Then what you do is, since you know that the object is surrounded by nothing, you set the outer parts of this trial image to nothing, set this area to 0, inverse Fourier transform it, and now you have some, for each pixel, you now have an amplitude and phase of each pixel that corresponds to this scatter pattern. What you do then is you use your experimental amplitude, but you use the phase that you got from here. After all, what you're trying to do in here is that when you record the scatter pattern with your CCD, you're recording the intensity of that scatter pattern, but you don't know what the phase of the light is at every pixel where it hit. If you did know the phase, you could just do a single Fourier transform and get the image. Here, you're iteratively finding what that phase is, and you rely on this so-called oversampling condition, which is just that the object is surrounded by empty space. You keep iterating this thing until you converge on the shape of the object that caused the scatter. Now, why is this so nice? Well, if you were doing this in an optical region of the spectrum, which you could, and people have done this, it's not dramatically useful because it's much easier to use a lens to get your image. But in the soft X-ray region of the spectrum, you know, your choices of optics are limited, and also they're very inefficient. This is a pretty efficient geometry. Everything, all you need is coherent light. The coherent light hits the sample, and then there's no optics between the sample and the detector. Now, this idea has an interesting history. It was first suggested by David Sear in the 1950s. And this was in connection with X-ray diffraction. He suggested that if you actually measured a diffraction pattern at a high enough spatial resolution of the detector, and you had enough computing power, you could probably infer what the phase of the light hitting this pattern is. The problem then is they didn't have linear detectors, they didn't have CCDs that could give quantitative data, and they didn't have anywhere close to the computing capability required to do this phase retrieval. And just to give you an idea what this requires, if you have just a single processor, Pentium 4 chip or something similar, it's about 2 processor weeks of time to do an iterative phase retrieval. So in the 50s, this was totally infeasible. But in 1999, John Yao's group showed that this was possible in a paper in Nature, where they used synchrotron light, they spatially filtered it with a pinhole, got a diffraction pattern, and reconstructed an image. But they used a synchrotron. It'd be great to be able to do this on a tabletop with a light source like high harmonics. And not only that, the high harmonic source is very useful because the light we get out is intrinsically fully coherent. So this is an imaging technique that's very well matched to this tabletop setup. And this is just a cartoon of what we have. We have our ultrashort pulse laser, which is takes up maybe a half or a third of an optical tabletop. Then we focus that light into our hollow waveguide that upconverts the light to soft X-rays. We have to reject the laser light, and we do this with a couple of very thin aluminum filters. The aluminum reflects the laser light, but lets the short wavelength light through. Then we just take that light and use a pair of mirrors to refocus the light onto the sample. And past the sample, we put a CCD. The resolution of this technique is still limited by the numerical aperture, but it's easy to get a very large numerical aperture in this geometry. All that means is that you put the sample very close to the CCD so that the CCD can catch light scattered to large angles. And this is a huge advantage for soft X-ray imaging because neither mirrors nor zone plates can handle very large numerical aperture imaging in the soft X-rays. So these are the first results we got from this, and this was published in PRL at the end of 2007, so just about a year ago. We took this sample. This is actually a thin carbon film that's used as an SEM grid. Actually, it's a TM grid. It's a grid for holding transmission electron microscope samples, so it's very, very thin carbon. This is a scaling electron image of that grid. We put that in the beam and we get this splotch here, and then we take that and put it through our phase retrieval algorithm, and we get this image. So you can see clearly that the structure here is coming out there. This looks a lot less perfect than this does, but in fact, much of what you're seeing here is the fact that this carbon is partly transmissive. So you're seeing variations in the thickness that don't show up in the SEM image. If you look at the resolution here, it's about 200 nanometers. So it's good resolution. It's not dramatically better than you can get with an optical microscope here. But that was the first result. If you work a little bit harder, in particular, it requires good samples. Here is a sample that was cut by Anne Sekdinawat, I think on a focused ion beam. It's a little stick figure woman with this line here is 1 microns. So this, for example, the hand here is about 100 nanometers. Interestingly, you see it's not there. We think it was just this SEM image is in reflection, so we can't necessarily see if the feature is filled in and opaque to the soft X-rays. But you take that and you record the diffraction pattern, you put it through the image reconstruction, you get a very nice image here. The resolution here is about 90 nanometers.
Henry?
Yeah.
Why is your diffraction pattern not symmetric there?
Not symmetric. Oh, you mean this is different from that?
Well, actually the one at 11 o'clock is the one that isn't symmetric. That one.
This thing, yeah, you're right. It's not. I never noticed that before, but I think my recollection is that the symmetry of the diffraction pattern depends on whether this is basically a binary image or not.
Just whether it's real or whether it has phase in it or not.
Right, that's right. So in it's something that's cut out like this, you wouldn't expect it to have phase. Like this image, since it does have phase shifts associated with it, it could be not symmetric. Why this is not symmetric, I don't know whether it's that there is some phase in here, or I'm pretty sure it's the right, the first thing I would guess is it's not the right pattern, but I think it is the right pattern because another thing, I'm going to talk about this a little bit more, but you can see that it's been, that these edges look a little funny, and that's a curvature correction. I know this is the amount of curvature correction necessary for this. It could be that this is kind of a garbage diffraction pattern that they took somewhere along the way and never substituted it in the view graph. But I don't think so. I think that this image is there. So, I don't know. I'll have to ask Richard. This works, gives 90 nanometers resolution, which is starting to get interesting. What we also did is we took the same microscope setup and brought it up to Colorado State. There they have an EV laser source that's pumped by an electric discharge. It has a wavelength at 46.9 nanometers, so it's a little bit longer wavelength, but it's a very bright source. Puts out almost no joule of energy in a single pulse. We use that for the lensless imaging technique. And what we did to get better resolution here is bring the sample very close so we can get a very large numerical aperture. This is the diffraction pattern. It's also not symmetric. Boy, that's a really good question. It's also not symmetric, but here, because we're capturing a large numerical aperture, we had to do a lot of this curvature correction. The optic still reconstructs, but and in fact, if you do a line out and look at the image resolution, here the image resolution is about 70 nanometers, so it's about 1.5 wavelengths. So it's getting near the wavelength limit for EUV imaging. But another interesting thing is that you can see a lot of background in here. The image has good resolution, but it's not quite as crisp as the previous image, right? This one has very good contrast. Basically, what we believe is going on here is that it's the different characteristics of the two sources. This source doesn't have quite as much spatial coherence, but it has a much higher temporal coherence, so a much narrower bandwidth. So the bandwidth does limit the resolution that you can extract from this lensless imaging. And also the coherence, the degree of coherence, and just how clean that beam is determines how clean the image is that you get out of it. A little bit more on the curvature correction. At first, we weren't doing curvature correction here, and this is the kind of deep involved image that you get. You kind of see that the edges aren't quite straight where they should be, and it actually, even though we're putting this through a computer algorithm, this almost looks similar to what you get from like a spherical aberration or something. It's not the same, but it's similar. The reason for that is that to do a good deconvolution, what you want to do is take a pattern that you got and project it onto a curved surface. Here we're recording it onto a flat surface. You have very high angle diffraction, which violates the paraxial approximation. But since everything here is done on a computer, you can resample the diffraction pattern from the flat CCD to a spherical field, and that allows you to go to very high numerical apertures. And this is one of the most exciting things about this lensless technique. Fundamentally, now we have an imaging technique that's not limited by either wavelength or numerical aperture. So it's a very interesting question, both with these tabletop sources and with free electron lasers, X-ray free electron lasers that are being built in a number of places. There's a real potential here to push optical imaging to resolutions of only a few nanometers. Okay, so this just shows what happens. You do the curvature correction. If you look at details in the diffraction pattern, you'll see that it gets crisper when you, even in the raw diffraction data, you can see that there's more regularity in the diffraction patterns. They look a little bit crisper, and then when you do the deconvolution, you get something that's much closer to what the real object looked like. Okay, so lensless imaging can also be combined with holography techniques. And there's an easy way to do holography with basically the same setup that we were using for lensless imaging. And what we do is something called the multiple reference Fourier transform holography. What you do is you take an object that's in a substrate where your object is in some sort of small window here, but then away from the center of the object window, you put a series of reference holes. So these are very small holes drilled all the way through the substrate. You illuminate this whole thing with coherent light. What happens is that your object diffracts light, but each of these reference pinholes generates a very nice, clean, diffracting spherical wave out of the reference hole. And if you then go down the line far enough to have interference between the object diffraction and the reference diffraction, that corresponds to a hologram. To make this technique more efficient for soft X-rays and for the type of source that we use, we take that sample and actually surround it by multiple reference holes. The data that you get corresponds to sort of a number of overlapping holograms. But the advantage here is that this is pretty efficient with photons, and it's just a simple fast Fourier transform to get the image out of this Fourier transform hologram data. The disadvantage is that you need to have these reference holes, so it's somewhat limited, more limited than a lensless technique. And also the resolution is limited to 70% of the size of this reference hole diameter. In other words, the hologram itself, if this hole is very big, the reference wave doesn't diffract very far. If you don't get interference information over a large numerical aperture. So that limits the resolution that you can get here to the reference hole size. But it does work, and you can do this with, this is just some of the data, the raw data that you get. Actually, no, this is raw data. This is the Fourier transform of this pattern. And what you get is a series of reconstructions of the original object. The other thing you can do, though, is take this data and put it through a lensless imaging algorithm. You can give the lensless imaging algorithm a head start by taking the hologram data. So you know something about the shape of the object from the hologram, but then you can use lensless phase retrieval techniques to extract resolution to extract information at higher resolution from the CCD data. So the idea is some of the data you have an interference between the reference holes and the object. That gives you lower resolution information. Other information is just diffracted light from the object that does not interfere with any of the light from those reference holes. So for that information, you have to do a phase retrieval. But that works, and we've shown that you can push the resolution then from 90 nanometers to about 50 nanometers, which is about 1.5 wavelengths of the 30 nanometer source that we used in this work. This really does have the potential for sub 10 nanometer resolution ultimately, but we're going to need shorter wavelength illumination light to get to these kind of resolutions. What this is already potentially useful for, let's see, yeah, I think we went over all this. This is just a resolution test here. What this is potentially useful for is 50 nanometers is about what the semiconductor industry needs for resolutions, for resolution in imaging photolithography masks for EUV lithography. So next generation microprocessors with very small feature sizes will probably use extreme ultraviolet light for the exposure. You need masks for that, and those masks, you be able to see what's there. So this resolution should be sufficient for that. We need to work on the exposure time, and this seems feasible that we can do this and make a microscope useful for this. There's also related work that we've been doing in taking some of these concepts of coherent imaging and bringing the time resolution aspect to it. This is a cartoon of some work that Mark Siemens has been doing in heat transport on the nanoscale. What he's doing in his experiments is he heats up an object which consists of very thin nickel lines on a sapphire substrate. And when you heat this with a laser pulse, the nickel absorbs light and it thermally expands, and then we take our EUV light and diffract it off this structure here. And what we're trying to understand here is essentially the cooling process. So if you dissipate heat from a very small structure into a substrate, the question is whether current diffusive models of heat transport work. And the reason why they might not work is that if your objects get small enough, the characteristic length scale of that object gets shorter than the mean free path of phonons in the substrate. So phonon mean free path, it relates to essentially the quantum aspects of heat transport. And what we can do then is diffract light off the structure, and what you see is a combination of both the thermal heat flowing into the substrate and also acoustic waves that are generated when you ping this surface with the short pulse of light. This is work in collaboration with James group in mechanical engineering here. We're just getting very interesting data that I'm not going to explain the details, but we do see this effect of it's so-called ballistic heat transport that you get when your object size gets small compared compared with this photon beam-free path. And one of the directions that this is heading is we can combine femtosecond time resolution with nanometer imaging resolution to look at various types of dynamics. This is a simple one-dimensional diffraction, but you can certainly do it in a phase retrieval imaging geometry. And we've also very recently shown that we can do this with magnetic materials. So we can look at magnetic domain orientation by reflecting UV light off the surface. Okay, well, where is this work going? A very exciting direction is to try to go to shorter wavelengths. And specifically, if you look at material absorption characteristics in the soft X-ray region of the spectrum, these lines here, this curve corresponds to the absorption length of water as a function of photon energy. And this curve here is for a typical protein. What you see is that the absorption length through water gets quite long, up until a photon energy of about 550 eV. That corresponds with the K edge of oxygen, which is the energy it takes to kick out a 1s electron from the oxygen atom. In the region below this oxygen edge, but above the carbon edge, carbon absorbs very strongly, and water is relatively transparent. These absorption depths are long enough that you can take a single cell and image through the whole thing and have very high contrast with all the biological material. So you can get very high spatial resolution and good contrast. And this type of soft X-ray imaging has been done quite a bit at synchrotrons. This is a good example of it. That's a movie. Let's see if I can click on it. Yeah. Okay, so this is an example of a tomographic image that was taken with synchrotron resolution of a single cell, where they've also done computer enhancement to single out various components of that cell. So this is a good ultimate goal for tabletop imaging in this wavelength range, to be able to do this. To get there, we need photons with energy about 300 electron volts. Right now, we're using about 50 electron volts energy. So we need higher photon energies. Right now, we can't do this with a tabletop source because we don't have the brightness. Now, one way of getting brightness is to build a big machine. This is another example of future applications of coherent X-ray light. This is taken from, I think, a website of the LCLS. LCLS is the Linux coherent light source. If you haven't heard about this, basically they're taking that Stanford linear accelerator, which is no longer useful for high energy physics, but they're taking that electron beam and making a free electron laser with it. So it's roughly a 2 kilometer long laser, but it generates X-rays, and it's scheduled to start up in the next year or so, and the goal is to generate coherent X-rays at up to about 8 kV energy. And the idea there is you take biomolecules, drop them into the laser beam. This is a big machine with lots of photons in a single pulse. Just diffract light off a single biomolecule, get a diffraction pattern, and reconstruct the structure. The idea here is that right now, X-ray crystallography techniques only work for biomolecules that you can crystallize. And a lot of them, they just haven't figured out how to do that yet. So here you can do it with single samples, potentially with atomic level resolution. This is very much a dream. I think people are thinking they're going to have to be really lucky to even do this with LCLS. And they need the next generation free electron laser, which will be a 30-kilometer-long LINAC that the Germans are thinking of building. But that's a $10 billion project. Obviously, if people are thinking about spending $10 billion on it, there's a lot of motivation for that. But we'd like to stick with doing things on the tabletop. So what we're trying to do is to figure out how to extend high harmonic generation to shorter wavelengths. How much time do I have? Probably another 5 minutes, 3 more minutes. Okay. I won't belabor this, but basically the trick to getting very bright beams from high harmonic generation at shorter wavelengths is not building a bigger laser, because I already showed you that scaling is linear with intensity. So to generate 300 eV compared with 50 eV, we need 6 times the intensity. Even our current lasers can do that no problem. The problem is phase matching. Basically, if you turn up the intensity higher, you're ionizing your nonlinear medium much more strongly. And it's the free electrons that you generate in the ionization process that cause a phase mismatch that makes the intensity of the light that you're generating go down very rapidly with shorter and shorter wavelengths. So currently, we can't generate enough light to do soft X-ray imaging. We have solved this problem now of phase matching, so it's a matter of working through technical issues. So the dramatic fall-off is due to phase-induced, plasma-induced phase slip. This is just a cartoon showing that as you try to look at the light that comes out at shorter wavelengths, the emission from different regions of your nonlinear medium doesn't add up coherently. You don't get bright light. So there are 2 techniques that we've now developed that solve this issue. One is, turns out if you drive the process with longer wavelength driving lasers, you improve phase matching to shorter wavelengths. It's somewhat counterintuitive, but we've shown that experimentally. Instead of using a Ti-Cephalor laser with an 800 nanometer wavelength, if we go to 1.3 microns, we've actually already shown phase match conversion into the water-linear region of the spectrum. And the other technique is so-called quasi-phase matching, where we actually set up complicated geometry that can phase match the process. So, I'll skip all of this, but basically this is just some data that show that as we go to shorter wavelengths, and then what we see is a very systematic shift in the center of the spectrum of high harmonic generation that's consistent with our calculations. And it also showed that in the case, for example, where we're doing higher harmonic generation in helium using 1.3 micron light, we see a phase matching cutoff that's just above the water window. And the challenge here is that the lasers that we have at this wavelength don't give as much average power. So now we have to build the right types of lasers to give us high average power at wavelengths in the sort of 1.3 to 3 micron region of the spectrum. And the other way we can do this is to use quasi-phase matching techniques. Without going into the details, this is just some data that show that quasi-phase matching works in higher harmonic generation. The way we implement it is we actually take the laser pulse that's generating the high harmonics and propagate a sequence of laser pulses in the backward going direction through this waveguide. Where the 2 pulses cross, you actually scramble the phase of the harmonic emission and essentially shut off emission from certain regions of space between this waveguide. If you do that in the right sequence, you can suppress destructive interference and actually get brighter emission out of the waveguide. So it's actually, we think now that the ideal is a combination of tuning the driving laser wavelength and using these quasi-phase matching techniques. What that'll let us do is get light that's bright and that's monochromatic. So quasi-phase matching selects out a narrow range of wavelengths, which is what you need for lensless imaging. So we think that now we know what to do to make the light sources bright enough that we can start to do imaging in the water window with the tabletop setup. And in fact, if you look a little bit harder at different techniques that we can do on paper here, it may even be possible, in fact, it looks feasible to use high harmonic generation to get light even up to the 10 kV range that the LCOS can generate. We won't generate as much light in a single pulse as they can do, but maybe we can get to comparable average powers of coherent X-rays and use a tabletop setup. And with that, I'll finish up here. Just the summary is that this process of high-order harmonic generation is an attosecond time scale process. It's the first really non-trivial dynamics that people have worked with that happen on a suboptical cycle time scale, which corresponds to attosecond time scale. This process was discovered only 20 years ago. We made a lot of progress, and I can see, personally, I think that we're following a pathway that's kind of analogous to the development of NMR, which originally started out as a quantum phenomena discovered in the 1950s. Then people started using it to do various types of spectroscopies, chemical spectroscopies. And now it's used for magnetic resonance imaging 50 years after it was first discovered. And I can see that that kind of progression is happening in this field as well. So with that, I'll finish and take questions. Thank you.
Questions?
In your lensless imaging setup, I noticed that you have a vacuum chamber in your imaging. It seems like you could easily improve your resolution by 1.5 times or so by having an immersion medium. Do you have any specific reasons for not doing so?
Immersion does not work at this wavelength range. The reason that we work in the vacuum chamber is because the typical absorption depth for light in this wavelength range is 1/10 of a micron. So it goes up to about 10 microns in the soft X-ray region of the spectrum. But none of this wavelength range will propagate through any significant distance in air, let alone in water. Plus, actually, you can image in the water window. I showed you some of those images. The index of refraction for the soft X-rays is actually 0.9994 or something like that. It's not 1.5 for this wavelength range.
In your lensless imaging, you seem to imply a sort of three-dimensional reconstruction of the tomographic formalism. But what you described for your phase reconstruction is conventional two-dimensional.
Yeah, that was not a lensless imaging technique. That used the zone plane to get that tomographic image.
Well, when you showed lensless imaging, you showed sort of some slices through the diffraction pattern, some sort of 3D.
Yeah, this is a very interesting topic. So people have done tomography with lensless imaging. You can take your object and essentially tilt it. It's small differences in angle. You get a sequence of diffraction patterns, and you can take all that data and stick it into the right algorithm and extract a 3D image.
So it does work in 3D.
It does work in 3D. That's a lot of That's a lot of, yeah, that's right. Phase retrieval does not work in 1D, but it does work in 2D.
And it also works in 3D.
Also works in 3D. But that's what John Meow was working with, and one of the most exciting things, he hasn't published this yet, so don't repeat it, but what they found is that in the case of very high numerical apertures, it looks like you do a single shot and get 3D image information out and actually successfully reconstructed it. They've done that with our data now because essentially our data was the first lensless data taken at very high numerical aperture. Then they started thinking if light scatters off an extended image, and if you're catching it out to large angles, there could be a phase shift due to the depth information. And in fact, that does work. You can take a 2D diffraction pattern and extract a 3D image out. You can't get more pixels, you can't get more voxels in your 3D image than you have pixels in your CC. So it doesn't violate anything, but it looks pretty interesting that that's possible. And that's important, has important implications for some of the LCOS stuff. Because if you're dropping a single ion molecule through it, you can only get a 2D image. That's a lot less attractive than getting a single shot 3D image.
Can you tune the wavelength of the X-rays coming out by temperature or changing the pressure of the wavelength?
Well, you tune it in a variety of ways, and all of the tuning basically relates to changing the phase matching conditions. So it's not quite a continuously tunable light source, and that when we have a sort of different regions of the spectrum that will, for example, phase match if you use helium gas. Helium phase matches have shorter wavelengths than argon or neon. Each of them generates well at a certain wavelength range. Now, in general, you get a whole spectrum of these harmonics out. So in the imaging, you pick out one of those harmonics to do the imaging with. But if you go back to the quasi-phase matching, here what you see is when you use these backward-going pulses, you can select out the wavelength that gets bright. What you're doing there is that every harmonic actually has a different coherence length. So you can tailor this pattern to make a certain photon energy the brightest. So this would be very versatile. If we can just program a pulse sequence and get the right wavelength out. And this data shows that that's possible. Right now, our students are constructing a pulse shaper that can give more sophisticated sequences than we can do now. This data, for example, this harmonic here, we enhanced by about 700 times using a 4-pulse sequence of backward-going pulses. And you can see that this one is bright, but the neighboring harmonics are fairly bright too. The larger the number of pulses in exactly the right spacing, which can vary in the pulse train, you should be able to select out a single harmonic, and also if you just reprogram, move around the wavelength.
More questions? So let's now yes. Thanks, Henry.
Okay, thank you.
We'll see you next week. Stay tuned for the location.